Okay, all right, let's get into it. Chemistry 3101. So we finished sections 6.1 to 6.6, which dealt with a lot of general chemistry 2 and a lot of general chemistry 1. Now this section should be new to just about everybody, the section on nucleophiles and electrophiles. And if you think about what a file is, okay, if you think about something that's like an audio file, it's somebody who's into stereo equipment or something, or maybe into, I don't know, fancy speakers or something. And so a nucleophile is something that likes nuclei, right? Something that wants a nucleus, and a nucleus is positively charged. And so nucleophiles are usually negatively charged. They don't have to be necessarily, but oftentimes they are. Whereas an electrophile, a file is something that loves something. So if you love electrons, electrons are negative. So electrophiles are oftentimes positive, and you can kind of think about it that way. So if you think about the reactions that we've done in this class, it says here that ionic or polar reactions occur when one reactant has an area of high electron density and the other reactant has an area of low electron density. Now, how would you know if something has high electron density versus low electron density? Okay, this is a good time to explain to you or show you how it's important that you understand things like chapter 1 very, very well, because in that chapter, the review of general chemistry, we went over polar and nonpolar bonds in detail. And so based on the idea that you guys understand bond polarity, you can take a look at a molecule and you can look for the region of high electron density or a region of low electron density. And so if we have negative charges, we know the negative charges based off of electrostatic attraction are going to be attracted to positive charges. And so what does that mean? It means if you have something that's electron rich, which is oftentimes negative, it's going to be attracted to something that is electron deficient, which is oftentimes, not always, but oftentimes positive. So take a look at these two molecules, okay? The one on the left is CH3Cl, okay? It's called methyl chloride. The one on the right is CH3Li, that's methyl lithium, okay? Two compounds look kind of similar, right? You get a CH3, a methyl, and then you've got a chlorine and a lithium. However, if you look at the molecule itself, okay, very closely, you see the tetrahedral geometry here. You guys should know by now that chlorine is more electronegative than carbon, right? Carbon, if we write out here electronegativity of carbon, carbon is 2.5, chlorine is up here 3.0, and lithium is going to be pertinent for us too. So these aren't in order, but anyhow, lithium is 1.0, and then of course hydrogen is 2.1. Anyhow, let's move on from there. So if you take a look at the bond between carbon and chlorine, there's a dipole, right? That's what this arrow means, because chlorine is more electronegative than carbon. You see the dipole is going towards the chlorine like that, okay? And you see that in the electrostatic potential map where it's orange, okay? This is a region of high electron density. Now, if we look at methyl lithium, it's got the same molecular geometry. Most of the molecule is the same, but now carbon is more electronegative than lithium, and so our dipole is going in the opposite direction. And you see that in the electrostatic potential map. The most of the electron density is down by the carbon, right? So we say in methyl chloride that the carbon is electron deficient, or you'd say it's electron poor, whereas the carbon in methyl lithium is going to be electron rich. So how do we tie that in with the term nucleophile and electrophile? So make sure you can sort this out in your brain, is that we say the methyl chloride is electrophilic. It's an electrophile. Why would we say that? Because the carbon is partially positive. So that means it's attracted to electrons, right? If the carbon is partially positive, that it means it wants electrons near it. It's electrophilic. It loves electrons. It wishes it had electrons, right? Whereas in methyl lithium, the carbon is nucleophilic. Why? Because now the carbon has a partially negative charge on it, so it's seeking a nucleus, right? Give me a thumbs up if that resonates with you even a little bit. The carbon atom is nucleophilic if it has a negative charge or partial negative charge, and the carbon is electrophilic even if it has a partial positive charge on it. There we go. Okay. So when we talk about nucleophiles, it's a way of saying nucleus lover. And I said a phile is somebody that's into something, like an audiophile. Okay, so nucleus lover. So a nucleophile is going to be electron rich, and it can donate a pair of electrons. So make sure you underline that. A nucleophile is able to donate a pair of electrons. Well, where do you get a pair of electrons from? It could be from a bond or a lone pair, right? Those both possess pairs of electrons. So if we take a look at nucleophiles and we think about them in terms of Lewis acids and bases, you should remember that a Lewis acid is an electron acceptor and a Lewis base is an electron donor. So that means that a nucleophile is also a Lewis base. Now, it says here more polarizable molecule, or sorry, more polarizable nucleophile is going to be a stronger nucleophile. If you don't remember the word polarizable, go back and look at it. It would have been covered in detail in chapter 1. So I told you that as you go down a group, as you go from oxygen to sulfur, let's say, the sulfur is more polarizable. It's able to distort its electron cloud because it's bigger. But anyhow, if you take a look at all the species on here, they're all nucleophiles, right? Remember, the nucleus has a positive charge. We see a partial negative charge on the carbon in methyl lithium. Definitely see a negative charge in ethyl oxide. Now, if you look at ethanol, there's no negative charge on here. However, I could draw a dipole in this direction because oxygen is the second most electronegative element in the whole periodic table. I could draw one like that too. So what's the conclusion? Is that my oxygen is partially negative up here. The oxygen is partially negative. So, excuse me, even though the oxygen doesn't have a full-on negative charge, it is still nucleophilic. Then we have a pi bond, right? Pi bonds, you know that pi bonds are weaker than sigma bonds. So a pi bond can act as a nucleophile as well. Now, if I was to compare ethoxide versus this sulfur anion here, so this is called a mercaptide. Anyhow, the name's neither here nor there, but you would say that this is a stronger nucleophile than this. Why? Again, because sulfur is more polarizable than oxygen. Okay, and this is going to come up more as we move on in the class. Anyhow, an electrophile, I'll go a little quicker now. An electrophile is an electron lover, right? Electrons are negative, so it's going to be something that's electron deficient. An electrophile is a Lewis acid, and you remember that a Lewis acid is an electron acceptor. Good, electron acceptor. So carbocations and partially positive carbon atoms are really good examples of electrophiles that show up all the time in this class. So if you take a look at the compound on the left, that's 1-chlorobutane. You can see the dipole here, which renders the carbon partially positive. So that's an electrophile. And then if you look at a carbocation, well, you know that a carbocation is sp2 hybridized. And so it's got an empty p orbital, right? And it's got a positive charge on the carbon. And so it's seeking electrons as well. So electrophile and nucleophile. Now, this example that's shown here is not rudimentary, but I'll kind of walk through it with you. And table 6.3 gives you some examples of nucleophiles that are common and electrophiles that are common. So as far as nucleophiles go, if you have a dipole between something like lithium and carbon, right? Carbon is more electronegative than lithium. So you can see the partial negative charge on there. So that's nucleophilic. The lone pair on oxygen, that renders it nucleophilic, right? You know that this oxygen is delta negative because oxygen is more electronegative than hydrogen. Then a pi bond, I said, is weaker than a sigma bond. As far as electrophiles go, the easiest one to recognize is always a carbocation. And then if you have a bond between carbon and something that is more electronegative than the carbon, like a chlorine, then that renders the carbon electrophilic because most of the electron density is near the chlorine. So if we were to take this species on the top, and again, it's not simple, I'll walk you through it, but I'll ask you guys a question, and it's not a trick one whatsoever. If I was to circle the hydroxyl group of this alcohol here, I'll even put in the lone pairs here, would you say that oxygen, what do you think the best definition for it would be? Would it be a nucleophile or an electrophile? It's got lone pairs on the oxygen. It's going to be a nucleophile. Exactly. Thanks, Rubio. Yeah, it's going to be nucleophile. Okay, let me try another one with you. Okay, what about this carbon? If I highlight this carbon in red, okay, I'll put the lone pair on the oxygen of the carbonyl. Do you think that carbon is a nucleophile or an electrophile? Just that one carbon atom. And remember, think about the dipole, right? Because it's attached to an oxygen. Exactly. It's going to be an electrophile, isn't it? Right? Because we have a strong dipole going towards the oxygen. And so that renders the carbon partially positive. And so this carbon would be an electrophile. Yep. What else? We have the nitrogen, and we know there's a lone pair of electrons on it. So it would be a good nucleophile. Nucleophile. What about, let's just talk about the carbon, okay? What if I highlight this carbon in blue? Okay, this one might be a little bit more challenging, but think about it. The oxygen has a positive charge on it, okay? Think about this whole portion of the molecule here. Is that carbon partially positive or partially negative? With that carbon in blue, would it be an electrophile or a nucleophile? Anybody? Yeah, exactly. Thank you. It's partially positive. This is actually a very strong electrophile. If you were to compare the carbon in blue versus the carbon in red, the one in blue is actually a stronger electrophile. So stronger electrophile. And the reason why is because, yeah, you've got the dipole going this way, sure, but you could also draw a resonance form now where you put the positive charge on the carbon, okay? So you can think about it that way. The last one is the oxygen with a negative charge. Well, obviously that's a nucleophile. It's negatively charged. Of course, it's seeking a nucleus, right? Something that's positively charged. And so we'll just write here, excuse me, nucleophile. Like that. There you go. So again, don't stress about memorizing these or anything yet. Like, oh boy, I have to memorize this and I have to memorize that. Trust me, once you get through all the practice problems and draw all the curved arrows, for all the suggested practice problems with nucleophiles and electrophiles, you'll start to recognize what a nucleophile and electrophile is. So we're going to switch gears now, and we're going to talk about using our nucleophiles and our electrophiles to draw reaction mechanisms, okay? When we have a reaction in organic chemistry, and we saw this in the acids bases chapter, right? Because we looked at all kinds of acid-base reactions, okay? But all the reactions that we're going to look at, not all of them, but greater than 90% of them in this class are what we call an ionic or a polar reaction. And when we have an ionic or a polar reaction, we can actually use curved arrows, a double-headed arrow, to show how the electrons move as the bonds are being broken and formed. And remember, we did this in chapter 3. Okay, we did this in the acid-base chapter in chapter 3, right? We showed a bond being formed. So this is a bond being formed between the hydrogen and the B, okay? And then we said that this is a bond being broken. So that gave you with the A anion over here. Now, this is something that comes out of our textbook, okay? So I'm just going to put here, and I'm going to give the guy the credit. The author of our textbook, David Klein, D. Klein, okay? He's the one who came up with these 4 main ways of pushing arrows in ionic or polar reactions. A nucleophilic attack, a loss of leaving group, a proton transfer, and a rearrangement. These are going to come up virtually Avogadro's number of times throughout this class, okay? A couple other things, I remember being a student and struggling with vernacular sometimes that my students or my instructors would use. So when we say drawing curved arrows, okay, sometimes we call it arrow pushing. And you're like, well, what are you pushing? Are you pushing it around with your finger? No, it's just what we call it. Okay, it's just a vernacular that we use. We say, draw the mechanism, draw the curved arrows. Can you do the arrow pushing for this? They're synonymous. Okay, so it doesn't mean you're like pushing an arrow around, like, hey, you get out of my way or something. It's just when we say arrow pushing, it means the same thing as curved arrows or drawing a mechanism. It's just showing how the electrons move during a reaction, showing how the bonds are broken, how the bonds are formed. And so let's start with the nucleophilic attack. And that's, we actually use the word attack. If you remember back in chapter 3, I would say the base attacks the proton on the acid, right? So this is vernacular that you might be used to a little bit. So let's take a look at this one here. It says nucleophilic attack is a nucleophile attacking an electrophile. We know the bromide, right? A bromide ion is nucleophilic. How do we know? It's got a negative charge. Of course it wants a nucleus, right? Nuclei are positive. And then we have an electrophile. Well, that's a straight-on carbocation. And you guys know that positives and negatives attract each other. Now, the tail of an arrow always starts on a pair of electrons. It can either start on a bond or a lone pair. Okay, but it has to start on a pair of electrons. Here you see the tail of the arrow starting on a lone pair. It doesn't matter which one. They just chose this one that I happen to have in the blue circle. So you see the tail starts on the pair of electrons that are making the bond, and the head of the arrow ends on a nucleus. Well, you can tell that this is the carbon it has to end up on because that's where the bonds form, and that's where the positive charge is. So then the electrons end up being shared. So it says here electrons end up being shared, and these are the electrons being shared right here. So the bond that I highlighted in green, that is the bond that was formed. So for a nucleophilic attack, what do we need? We need a nucleophile, and then we need an electrophile. Now here's another example here. It says that a nucleophilic attack might require more than one curved arrow. The last one, we just had one curved arrow, nucleophile attacks electrophile, you're done. This one is going to require more. Why? Because we know that carbon cannot have more than 4 bonds. That's impossible. Okay? And this is a bond being formed. It's starting on the lone pair of an oxygen. Why? Because an alcohol, this oxygen, is a good nucleophile. If you don't believe me, let's think about it. There's a dipole going here, and there's a dipole going here. So the oxygen is partially negative. It's not full on an anion, but it's partially negative. So the tail of our curved arrow starts on a lone pair because that's a pair of electrons, right? Now, if you look at this species here, this is called acetyl chloride or acetyl chloride. If you're wondering, why does the head of the arrow end up on this carbon? Why doesn't it end up over here on the chlorine? Let's think about that. Where are the dipoles? There's a dipole going towards this oxygen, and there's a dipole going towards this chlorine. This carbon that I have highlighted in blue, that carbon is by far the most delta positive thing in that whole entire molecule, right? Everybody's pulling electron density away from it practically. And so that means that that carbon is a very big delta plus. So I'll just put delta plus like that. So nucleophile attacks electrophile. But again, why are there 2 curved arrows? Because if I was to just stop and not put this curved arrow, then the carbon, watch my green pen, it would have 1, 2, 3, 4, 5 bonds. Carbon does never have 5 bonds. And so you have to break that pi bond simultaneously. So when you have reaction arrows occurring at the same time, we say it's a concerted process. So the nucleophilic attack, and then we break this pi bond, and we put the pair of electrons up on the oxygen. And remember, when oxygen has 3 lone pairs and 1 bond, it has a negative charge. And then, of course, the oxygen from your nucleophile has 3 bonds and 1 lone pair, and so it has a positive charge. So there you go. That's a nucleophilic attack of this alcohol on this acid chloride. Let's take a look at another one. It says pi bonds can act as nucleophiles. This is something we won't actually look at, this one here, until chapter 18, but we will see other examples of pi bonds behaving as nucleophiles in this class. You guys remember, I might have told you this, I can't remember if I did or not, but an aromatic ring, if I haven't told you yet, aromatic doesn't mean that it's necessarily a fragrant compound, like a perfume or something. Aromatic just means that it is very stable, okay? But if you put an aromatic ring in the presence of something that's a very, 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 very powerful electrophile, it's going to react like, it's going to behave like a nucleophile. So check this out. This molecule here, this is called sulfur trioxide. If you draw the Lewis structure, which is already on the page here, okay, you guys know the oxygen is the second most electronegative element in the whole periodic table. So that means there's a dipole going this way, there's a dipole going this way, and there's a dipole going this way. That sulfur is like delta plus. It is so positive, partially positive charge, that when it sees an aromatic ring, the aromatic ring is like, I can't help myself. I got to react with that thing. That thing is so positive. And so it says here, notice that only one of the carbon atoms from the pi bond uses the pair of electrons to attack the electrophile, and the other one, so this one gets attached to the sulfur, the other one now becomes, excuse me, a carbocation, like that. All right, give me a thumbs up if you're with me on nucleophile and electrophile. Is everybody, even if you're like 60% of the way, it's good enough. You're going to have to repeat it a lot. Okay, Nucleus lover, negatively charged. Electrophile, positively charged, or at least partially positive, partially positive. Okay, so now we finished nucleophilic attack. So I told you there was 4 patterns. The second one is loss of a leaving group. Okay, the loss of a leaving group. You know how this morning we talked about bond dissociation energies and homolytic bond cleavage? Well, the loss of a leaving group is actually a heterolytic bond cleavage, meaning both electrons go to one of the atoms in the bond. So here we have, this is called tert-butyl bromide. You see that this bond is being broken, and both of the electrons are going onto the bromine. So now the carbon becomes a carbocation, and the bromine becomes a bromide, okay? And oftentimes we can have multiple curved arrows that we use to show the loss of a leaving group. This is something that you won't see until organic 2. This is actually called an SNAR reaction. It's not pertinent for this class whatsoever, but you see that the leaving group here, this chlorine, is leaving. And if you get some, if you try practicing the curved arrows here, maybe I'll just draw the curved arrows, they're the result of the curved arrows rather. So if you draw what's left over after all these curved arrows are done, which is good practice, you end up with the chloride being gone, right? It's the leaving group, okay? We have a pi bond here, here, here. Then we have a single bond to our nitrogen. We have a single bond to this oxygen, which is negatively charged. And then we have a double bond over here, like this. There you go. So loss of leaving group. So this, the chloride, is the leaving group in this case. Now, so that's a leaving group. If you don't remember what a good leaving group is, I'll help you here. Or if you don't know what a good leaving group is, I'll give you a definition that you can write down. A good leaving group is the conjugate base of a strong acid. There you go. That's the definition of a leaving group. You could call it a weak base or the conjugate base of a strong acid. Either one is totally fine. So think about chloride. Chloride is the conjugate base of hydrochloric acid. That's a very strong acid. So that means that chloride is a good leaving group. All right, proton transfers. We did see these in chapter 3 in the acids bases chapter. Acids and bases chapter. We saw all kinds of proton transfers. So here you see this carbonyl is behaving as a base. Why? Because it's accepting a proton. The hydronium is acting as an acid like this. So you end up with the conjugate acid. Conjugate acid. In this case, water would have been your conjugate base. Conjugate base. Like that. Anyhow, but it recalls you need 2 curved arrows here. And it says the deprotonation of a compound is sometimes just shown with a single arrow. So meaning this is something that you might see on the internet. It just shows 1 curved arrow. It's not actually proper. So I'm going to put do not do this. Do not do this. Even if you see it on the internet, it's not proper. Again, organic chemists are like everybody else. They have bad habits, okay? I'd say that's borderline a bad habit, and I'll never do it, okay? If I draw a curved arrow, I'll do it in the proper way, and I'll show you the base that's picking up the proton, etc. So multiple curved arrows may be necessary to show the complete electron flow when a proton is exchanged. So we have the hydroxide ion here picking up the proton, and then you see we're forming a double bond here and putting a negative charge on the oxygen. So the result of this curved arrow, or these curved arrows, I'll just write it off here to the left a little bit. It's going to look like this, where you'd have a double bond like this, and your oxygen would have 3 lone pairs. And then, of course, you have your water after the hydroxide has picked up the proton. So it says here, something like this. This is kind of like a proton transfer combined with a resonance at the same time. But anyhow, we're going to get some practice on those as we move forward. And the last one, so we've covered nucleophilic attack, loss of leaving group, proton transfer. The last one is a rearrangement. It says here, if you have a carbocation, it's actually stabilized by neighboring groups through orbital interaction that we call hyperconjugation. So this is a word that comes up over and over in organic chemistry. I'll just say people usually kind of forget this word, but it is important. And what it means is that you guys know that Beatles song, I Get By With a Little Help from My Friends, right? So The more carbons that your carbocation is surrounded by, right? So this one would be tertiary, this one is secondary, and then this one here, this would be primary, and then this one, if you have a methyl, so if you go primary, secondary, sorry, tertiary, secondary, primary, down to a methyl, the tertiary is the most stable, secondary second, primary, and methyl is the worst of all, okay? And the reason why is because in order for the carbocation to be stable, it has to have more carbon atoms attached to the carbon with the positive charge. Okay, so the more carbon-based groups you have on your carbocation, the more stable it is. And so hyperconjugation explains the trend, and this is the trend that I just put on the previous slide. Okay, it's nothing new. I wrote it before. So increasing the substitution on your carbocation increases its stability due to an increasing number of adjacent sigma bonds aligned with the empty p orbital. I'm never, ever going to quiz you on this kind of orbital overlap here, but make sure you read it. You might find it useful, but I never quiz my students. I just want them to know the trend. So know this trend, okay? Make sure you're perfectly aware of that trend. All right, so now that we've got that, it says here, when would you see a rearrangement? Okay, so if you're not paying attention, wake up because this is a pretty important section here. Okay, there's two types of carbocation rearrangements that are common, and we see them quite a bit in this class. Students are usually very good at identifying. The first one is what we call a hydride shift. Okay, so here we have a secondary carbocation. Okay, can everybody see that secondary carbocation, meaning this carbon is attached to 1, 2 carbons? Give me a thumbs up if you see that. Yes? Okay. So what you do is you look at the neighboring carbons. So I have this next door neighbor in yellow. I have this next door neighbor in green. They both have protons on them. The one in green has 3 protons. The one in blue, or the one in yellow, has 1. If the proton from the yellow carbon moves over by 1, now I go from a secondary carbocation to a tertiary carbocation. Now, if you're wondering, why wouldn't a proton come off of the green one and switch? Because if that was to happen, what you would end up with in that case would be this, a primary carbocation, okay? And that is, so if you were to move one of these protons, you'd end up with this, and this is not stable, okay? Primary carbocations are not stable whatsoever. So now you're going from secondary, which is pretty good, to a tertiary, which is way more stable. And so that is going to happen spontaneously. Give me a thumbs up if you're with me on the hydride shift. So a hydride from a neighboring carbon is going to come over and produce a tertiary carbocation. Good, okay? And the next one is a methyl shift. And this is the same rationale here. Here you have a secondary carbon, and it doesn't occur for an ethyl or a propyl, just a methyl. If you have a methyl on the neighboring carbon and it comes over and you go from a secondary to a tertiary or from a primary to a secondary, it's going to happen because you end up with something more stable. So something about rearrangements I would put is this. If it can happen, it will. Okay, there's nothing you're going to do to prevent the carbocation rearrangement from occurring. If it can happen, it's going to happen, okay? So these are the two most common, and these are the ones that you need to know for Chemistry 3101. Are there others? Yes, but they're not relevant for our class. So what you're going to see is in a reaction like this one here, where we go from this alcohol to this alkyl halide, sometimes we have to combine a whole holy host of curved arrows, okay? Take a look at the first one. The first one, we have a hydrogen atom being added to the oxygen, so that's a proton transfer. Then we have water leaving, so that's a loss of a leaving group. Then we have a methyl shift, so that's a carbocation rearrangement. Then we have bromide acting as a nucleophile. This is our electrophile, and so we get a nucleophilic attack. And so you've got to be able to recognize those patterns. Often, we'll have 2 of the patterns occur simultaneously. Here you can see that in the first, or the curved arrow here, the long one, this is a nucleophilic attack, right? The hydroxide is a nucleophile. This carbon here is delta plus, so it's an electrophile. So we have our nucleophilic attack, but then the chlorine is leaving as a chloride. And so this one here, this would be our loss of leaving group. So we have nucleophilic attack and loss of leaving group occurring simultaneously in this particular case. So now what we're being asked to do in this question is, It says, for the following multi-step reaction, read the curved arrows and identify the sequence of arrow pushing patterns. Remember, we have 4 patterns. We have nucleophilic attack, we'll use Na. We have proton transfer, we'll use PT for that. We have LLG, which stands for loss of leaving group. And then for rearrangement, we use RGT. Okay, so you can use those abbreviations with me. I'm totally fine with them. They're the ones that David Klein uses. Okay, so we've got a total of 1, 2, 3 steps occurring here. Could anybody tell me which one of these 4 patterns is occurring in the first step? I'll give you a clue. There's only one of them occurring. I wouldn't. There you go. It's a proton transfer in the first one. Exactly. So it's a proton transfer, right? Because you have the hydroxide, which is a base. And if you're like, well, I thought you said it was a nucleophile. It is. Hydroxide can be a base or a nucleophile, depending on the situation. But you see the hydroxide is picking up that proton, and then there's a lone pair going on to this carbon. So that would be a proton transfer. What about the second one? The second step. How would you describe that one? Would that be a proton transfer, nucleophilic attack, loss of leaving group? Exactly, it's going to be a nucleophilic attack, right? Because this carbon with the negative charge, this is our nucleophile. Okay, if we look at the ester, you've got a dipole going this way and a dipole going this way. And so this carbon is delta plus, so this is our electrophile. And so this step is going to be a nucleophilic attack. The nucleophile is attacking the electrophile. All right, what about the last one? You see that you're losing this, you see the negative sign, that means losing, or it went away. So how would you describe the last one? A loss of leaving group, exactly, exactly. And the last one, you're losing the alkoxide, so it's a loss of leaving group. All right, now I've taught the class long enough to know that sometimes students will look at this question and be like, oh, what just happened? And that's totally normal. So if you're struggling with it, like I was telling you before I started recording today, you must practice with pencil and paper. It cannot be learned by looking at it. It's impossible. I mean it. It would be impossible. So drawing a curved arrow starts on a pair of electrons. I already told you this. It either starts on a bond or a lone pair, one or the other, okay? If you take a look at the curved arrows that are drawn here, okay, we see we have our nucleophile, right? Here we have an electrophile. And here, so this first curved arrow, this is a nucleophilic attack. This one is a loss of the leaving group. But you see that the tail of this arrow starts on a pair of electrons on the oxygen. The head of the arrow ends up on an atom in the ethyl chloride. This tail of the second arrow ends up, this tail here starts on a pair of electrons in this bond. And then the tip of the arrow, or the head of the arrow, ends up on an atom. So we have our nucleophilic attack and our loss of leaving group happening simultaneously. If you look at the example on the bottom, if you were to put in the lone pairs here, there's technically nothing wrong with the first curved arrow. This is a nucleophilic attack, but this curved arrow is not correct because the tail starts on an atom. It doesn't start by a pair of electrons. It doesn't start by a bond or a lone pair. It says here it's on a positively charged atom, right? Because this carbon here is delta positive because there's a dipole going towards the chlorine. And so that would be a huge no-no. So I'll put a big fluffy red X on that. All right. Now, as far as where the arrow ends, as I told you, it ends up on a nucleus. So the electrons can become a lone pair, or the electrons can become a bond between two nuclei. So if you take a look at this one here, so we have forming a bond. So this is our nucleophilic attack. This is our loss of leaving group over here. But you see that when we formed a bond, This is the bond that we formed here, okay? It came from this pair of electrons right here. And then we have the last pair of electrons from the bond, this bond, ending up as a lone pair on the chloride. Now it says never avoid breaking the octet rule. Never give carbon, nitrogen, oxygen, or fluorine more than 8 valence electrons. That's a huge no-no. So if you were to draw something like this is a violation of the octet rule because you're forming a bond, right? With the curved arrow, you're forming a bond, but then this carbon would have 1, 2, 3, 4, 5 bonds. You can't do that. So that's why the loss of leaving group is drawn simultaneously, right? This is your loss of leaving group, because that way you avoid giving the carbon an excess of electrons. You avoid breaking the octet rule. Anyhow, any curved arrow that you draw moving forward should describe one of the patterns that you've seen, one of the 4 patterns, like nucleophilic attack, loss of leaving group. If you look at this arrow shown down here, it doesn't have anything to do with anything. Okay, it breaks the octet rule, and it doesn't match any of the patterns, right? This carbon, for the head of the arrow, already has 8 electrons, so you can't add 2 more electrons to it. That's a violation of the octet rule. So every time we draw curved arrows, most of the time, we'll identify them as being nucleophilic attack, loss of leaving group, proton transfer, or rearrangement. So let's see if we can draw the curved arrows for this reaction. First thing I'll do is I'll put in my lone pairs that are missing. There's 2 lone pairs there and 1 lone pair here. So between the carbocation and the water, could anybody tell me which one of these is going to be my nucleophile? Will it be the carbocation or the water? Which one is the nucleophile? Yeah, the water is going to be the nucleophile. So this will be my nucleophile. That means that this is going to be my electrophile. Okay, this carbon is positively charged, no doubt about that. And the oxygen in water is partially delta negative, right? There's 2 strong dipoles going towards the oxygen. And so where is the tail? Could anybody tell me, like describe it to me? Where is the tail of my curved arrow going to start? Because you can see that I'm forming this bond here, right? That bond that I just drew in green, that is the bond being formed. So where on a lone pair, exactly. So the tail of my arrow is going to start on the lone pair on the water. Where's the head of my arrow going to end up? Exactly. It's going to end up on the carbocation, just like that. There you go. So how would you describe this curved arrow? There's only one. Would it be? Which one of those patterns is being described? Thank you, Jenny. Exactly. This would be a nucleophilic attack. There you go. All right. Awesome. So carbocation rearrangements, going back to this whole idea of the rearrangement, if you remember what I told you was, if it can happen, it will happen. If you take a look at this carbocation down here, there's nothing wrong with it whatsoever. If I draw a proton here in red, and I draw this proton here in blue, okay? Because remember, you can only look at neighboring carbons. Ask yourself, is a hydride shift going to occur here or a methyl shift? Will either of them happen? If you were to move the proton in red, okay, it's not a very good curved arrow, but if you did it, what you would end up with would be this. So you'd end up with this. So that would mean you go from a secondary carbocation to a secondary carbocation. Is that going to happen? No, that's not going to happen because you're not making something more stable. So this is not going to happen. What about the blue proton? Is that going to undergo a hydride shift? Could anybody tell me without me drawing it already? Yeah, absolutely, right? Absolutely it will. So it's going to look something like this. So now we've moved the blue proton. So now we have the positive charge here. So now we go from secondary to tertiary. And so is this going to happen? Oh, you bet your Bobby socks it will. Yeah, absolutely that's going to happen because you end up making something that's more stable. All right, so remember, you got to keep track of your hydrogens, right? If you're still struggling with bond line structures, you have to remember there already is a proton here. So now this carbon has a total of 2 protons on it, right? So you got to kind of keep that bookkeeping going in your mind. All right, so like I showed you, this is the answer, everything that I just showed you here. But the bottom line is it's only going to happen if you make something that is more stable. You have to have something that's more stable. And there's another interesting bit of information on here. Check this out. It says a tertiary carbocation, will it rearrange? The answer is possibly. It says here it's not going to rearrange unless a resonance stabilized cation is formed. So check this out. Here we have a beautiful tertiary carbocation. And you might be tempted to say, well, it's tertiary, it's not going to rearrange. Why would it do that? However, if you do this proton transfer, look at what happens. Now you end up with something that's tertiary slash allylic. So not only is it tertiary, but it's resonance stabilized. What do we know about resonance? It stabilizes the molecule. So yes, a proton transfer can occur if you take something from being tertiary to tertiary allylic, meaning it's even further stabilized. It's even more stable than it was before. So I'll just level with you when it comes to carbocation rearrangements. Students, you have to keep your eyes open and just keep them peeled for a carbocation rearrangement at all times because it's always possible. But usually you get very good at deciding, okay, yes, it's going to happen, or no, it won't happen. All right. The last section deals with reversible and irreversible arrows. This is a great section because it's not like an elephant in the room, but it's something that students will even ask me long before we get here. They'll be like, Mr. Dion, why is it sometimes that you draw reversible arrows and sometimes you draw irreversible arrows? Well, it's a great question. Okay. So reversible arrows are equilibrium arrows, and those look like this. Okay, nothing new there. And then if you have irreversible, that just means an arrow going in one direction, okay? Well, you see these arrows here are reversible. This one's irreversible. And the question as to whether you draw which one is actually a question of kinetics and thermodynamics. So let's take a look. Here are the rules. If the nucleophile attacking your electrophile happens to be a good leaving group, it's reversible, okay? So in this case, water is a good nucleophile, but to a carbocation. But it's also a very good leaving group because it's the conjugate base of hydronium, which is a strong acid, right? Hydronium has a pKa of about -2. Okay, it's close to -2. This is supposed to be about, so it's close to -2. So yeah, water is a really good leaving group, and so that means that the reverse process is going to happen. So in this case, we draw equilibrium or reversible arrows. Okay. The next one is if your nucleophile is a terrible leaving group, it's not reversible at all. You just draw an irreversible arrow. Think about this, okay? This methide ion. Is that a good leaving group? Well, it's the conjugate base of methane, which has a pKa of 50. So is that a good leaving group? That's like the worst leaving group in the universe, okay? So of course it's not going to leave. So in that case, the reverse reaction doesn't happen whatsoever, okay? So you have to know your strong acids. If something is the conjugate base of a strong acid, it can also act as a leaving group, so you draw reversible arrows. If it's not, then you don't draw them. The next one is the loss of a leaving group. If you just have a loss of a leaving group, it's virtually always reversible. So your leaving group can pretty much always come in and act as a nucleophile. However, if you're wondering, well, how am I going to distinguish between nucleophiles and bases and good nucleophiles and weak nucleophiles and good leaving groups and poor leaving groups? Again, that's going to be covered in more detail in chapter 7. So we're just kind of fleshing out the idea right now. But the bottom line is that weak bases are good leaving groups and strong bases are poor leaving groups. So remember the way I framed it was conjugate base of strong acid. That's a good leaving group. And so those can also act as good nucleophiles. And the last one is a matter, I think this is the last one. No, it's not. Sorry. This one here, the next one is for proton transfers, is a matter of pKa difference. If the difference in pKa between your acid and your conjugate acid is 10 pKa units or more, then you just say it's irreversible. If it's 10 or less, you just draw reversible. That's it. Here you see the difference is what, 34, 34.3. You see the difference here is what, 2.3. So the one on the top, irreversible. The one on the bottom, reversible. Then what I told you for carbocation rearrangements, if they can happen, they do. And so carbocation rearrangements are always, it says generally, it's pretty much always irreversible because there's no reason for them to go backwards. Okay, you wouldn't go from something less stable to something more stable to something less stable. It doesn't happen. Why would it do that? Okay, so thermodynamically, there's no driving force for a carbocation to become less stable. And this is the last one here. Okay, if you have a reaction where you form a gas, okay, so you guys should remember the N2, okay, the nitrogen, right? This is nitrogen, which is a gas. Gases are released as bubbles, right? They become bubbles. And once bubbles leave the reaction mixture, they don't come back, okay? They don't come like, oh, find my way back to the reaction. No, they're gone to compound heaven, okay? They fly away up the smokestack, up into the stratosphere. So if you lose a gas, it's irreversible. The gas is not coming back. So, students always like the ones where it's a gas because there's no question, okay? It always is irreversible, and that's it. However, I am your teacher, so I'll just tell you that when it comes to reversible and irreversible reaction arrows in Chemistry 3101, or even in 3111, it's usually not something I give my students a hard time about. The main thing that I want you to know is nucleophilic attack, proton transfer, loss of leaving group, and rearrangement. I don't pick on my students about reversible and irreversible arrows, but again, here's the information, and you could be quizzed on it in quiz 6 or the final exam. I'm just saying, when I grade a mechanism on a paper exam, I usually don't take points off for reversible or irreversible unless it's something particularly egregious. I don't beat my students up on that. The subject is difficult enough already.